that you can understand those simple effects of why it is proportional to mu phi and mu, or when mu phi is 0, why this is 0, when mu is 0, why this is 0. And so is the effect for the vorticity. It can all be understood from the simple general physics. There's an alternative approach done by two groups. The first one, this came earlier. The first one was done by Sun and Yamamoto, and the second one is by Stepanov and Yin. And they use the so-called Berry phase approach. So I'm going to give you a short introduction about what Berry phase is. It's actually very easy. Suppose you have a Hamiltonian, which depends on time, but the change of Hamiltonian with respect to time, the time scale is longer than any other scale in the problem. We call it a diabatic extension. Then in this process, suppose you start from a ground state. Then the state will generate a trivial phase, which goes like exponential minus IET. You just get it from, say, Schrödinger equation. But there will also be a non-trivial phase get generated during the process. Okay. And I want to link this into the example that you have already done that you are already familiar with. A Foucault pendulum. If we have a simple harmonic oscillator on Earth, and because Earth is rotating, so the plane that the simple harmonic oscillator is moving, the mass is moving, is actually going to be rotating for an observer on the Earth, right? This is the familiar physics of Foucault pendulum. It's interesting that the setup is in a cathedral. So he says that the science is actually going back to the church. And then you can ask a question. Suppose you shrink the pendulum smaller and smaller, and at the end it's just an electron. So we are going to talk about a microscopic Foucault pendulum. It's an electron on Earth, and there will be magnetic field on Earth, some geomagnetic field. And the magnetic field is going to align the spin of the B field, the spin of the electron. And the B field is actually rotating because the B field is fixed to the Earth. So the Earth is rotating, the B field is also rotating. After one day, the B field comes back to the original direction that it starts with 1 day ago. But the claim is now this electron will develop a non-trivial phase in addition to a trivial phase that goes like exponential minus IET. And this phase is the Berry phase. And in some cases, the Berry phase is related to some topological objects, which I'm going to talk about. Is going to be related to some co-and-co Berry curvature, or it looks like some magnetic field, magnetic flux of in the surface enclosed by the path in the parameter space. It's a long sentence. I'm saying that the Berry phase has some geometrical meaning. I'm going to give you more explanation here. So this is a simple explanation or description of the Berry phase. Suppose we have a system in ground state, but Hamiltonian is evolving in time. And suppose as the state goes from time to be you keep track of the matrix element of the time evolution for infinitesimal amount of time, delta t. So you start, this is your initial condition, this is your initial state, this is final state. And the time evolution is infinitesimally small. And suppose the initial state is a ground state, and we set the ground state energy to be 0. We can always do that. And so is the final state. So the matrix element, the forward matrix element, in both cases are 0, but not the forward 1. So for this matrix element, if we go back to the exponential form, then it looks like exponential minus I delta t times something. Okay, so let's call it AT. So there will be something that with some exponential form. And if the state is evolved in time, involved in finite amount of time, then the state is going to pick up a non-trivial phase that goes like this, with P to be some path ordering. Don't worry about this. And this looks like something you should be familiar with, especially when I turn into the next page, when we go to higher dimensional space. Suppose I have a free massless fermion, then the right equation tells you that it's Hamiltonian, goes like sigma that pp is the momentum, sigma is the Pauli matrix acting on the spin space. And suppose the particle is moving in the momentum space. And then it is similar to the example I showed you previously, but you just go from a one-dimensional space in the parameter space T to three-dimensional in P. And then the Berry phase can be written in this non-trivial form. It goes like A mu times it's a line integral of the gauge field. And you immediately understand that this is just the Harmon form effect phase. This goes like a magnetic flux. It is the magnetic flux enclosed by the closed path. And so let's consider this as a gauge field, and this is gauge invariant. It's coming from a magnetic, this is actually a magnetic flux. It's actually a magnetic flux corresponding to a three-dimensional monopole in the momentum space. The monopole means that it's just like an electric charge. Here is the magnetic charge in the B field space. So you have a magnetic charge in the origin of the P field, in the P space. So this non-trivial phase to the ground state can be described as a new term in the Lagrangian. And in a semi-classical approach, this new term will give a force in the equation of motion. And this force actually is equivalent to a source or sink in the phase space. Okay? And the source and sink will induce particle non-conservation, which is exactly what you want in an outlet. So this is the connection. Now here comes when Mr. Berry meets Mr. Wigner. Now I come to our contribution here. So in the Berry phase approach, it is a Hamiltonian approach. It's not manifestly Lorentzian covariant. And the Berry curvature is coming from a three-dimensional monopole in Euclidean momentum space. While in the Wigner function approach, it's fully Lorentz covariant. And the monopole goes like it's a four-dimensional monopole in Euclidean space. Those two approaches, actually, their formulations seem very different. But we show that they are actually the same. And we actually made a dictionary of the two. We can go from the 4D case to the 3D, from Wigner to Berry. So the idea is very simple. Just impose unsure conditions in the momentum space, then integrate out those redundant, the zero component of the momentum, and then you can reproduce all the equations from the three-dimensional case. Let me show you. But you also got new dependence. Those volticity dependence is new. So as I said, we work in a limit where particle collisions are neglected. So the right-hand side of the Boltzmann equation is 0. This is the collision term. It is 0. On the left-hand side, it describes how a small volume in the phase space moves in time. And those critical depends on the equation of motion in the semi-classical approach. And the equation of motion has this complicated form, including dependence from the B field and in the product with the omega. Omega is the Berry curvature, so it's the Berry magnetic field in this case. And so if we turn off the omega dependence, then we recover the previous results derived from the Berry approach. But we start from the Wigner approach, we recover all this omega dependence, which is new. This is for experts only, but so I'm going to skip this first, unless you ask questions. So, what is this good for? There is an experiment in Brookhaven.
I'm sorry, may I stop you again for a while? So, you start with massless QED.
Yes.
You would like to calculate all those coefficients, transport coefficient, CB, so on and so forth.
That's
okay.
Right.
Now, where do you, then you are telling us that Berry's approach and the Wigner's approach are different. at what point you choose that I follow Berry or follow Wigner? Where?
Okay, I actually try to claim that those two approaches look very different, but in our paper we.
I mean, at what point? For example, presumably, I mean, when I see your Wigner's formula.
Yes.
Okay, I may be able to think of it in terms of, let's say, diagrams, right? Okay, yeah,
that's right.
This one.
Yeah.
Okay, and then in Berry space, what should I?
Okay, in Berry space approach, you think about how you can get a non-trivial Berry connection. How you can get something that's similar to a Berry connection, which is corresponding to the change of the spinner. If you change momentum, the spinner are different now. I would say the concept is quite different.
Presumably it is simpler, right?
Yeah, here is simpler, but you get less result.
You get
less result.
Less.
Yeah, the vorticity dependence is hard to get from here.
I see. And you will be telling us that still, in your approach, the Berry space, the Berry approach could still get you right.
Okay. What we did is to start from Wigner to Berry, so
see.
we get more results than what usually people just start from Berry.
Okay.
And in the meantime, we
so
showed that
Wigner's
the two
approach is always
are the same.
correct, always rigorous, right? That's the default approach,
That's
right?
right.
Presumably, from quantum field theory point of view.
That's right.
Okay. I will tell you something about the anomaly of Berry space connection later, maybe, because that's seems not to be the major point of your talk. So
Okay. All right.
there exist problems with the connection.
Okay. We can talk about this later. So experimentally, there are some curious experimental result called charge separation in heavy ion collision. So if you collide two heavy nuclei to go to collide together, so you collide them, and after collision there's a small fiber, and it is spinning, so there's some residual B field pointing in the Z direction. It turns out you will see more positive charge particles in one hemisphere, but more negative charge particles on the other. And this kind of effect claimed to be able to be explained by the chiral magnetic effect, which is the current, chirality current driven by the B field. But this is still too early to see whether that is the most dominant contribution. So I just mentioned this. So let me briefly summarize this. Since I still have some time, I want to briefly talk about another work on coatoms. So, wow. So in this approach, a new and manifest relativistic chiral kinetic theory is obtained. In this theory, chiral magnetic effect, vorticity, chiral anomaly, Berry phase, and Berry monopoles are all described in a unified way by the Wigner function. So we are still developing along this direction. So this will be short, in 5 minutes. So when the imagery is a real alternative, this is in collaboration with Jens Braun in Darmstadt University. Freeman is in the GSI, also in Darmstadt. Joachim Druth is at North Carolina University. Deng Jie is in Shandong University. He was a postdoc at NTU. And Ma Chende is now at NTU. Cai Yudai was here for his undergraduate, and then went to Tsinghua, then he is in Cornell now. So this is a schematic QCD phase diagram. I emphasize it's schematic because we actually don't know the details about this phase diagram. So this is the temperature axis, and this is the chemical potential. You can think about this to be correlated with density. And so at low temperature and low density, this is a hadronic phase. And high temperature or high density, this is a quark-gluon plasma phase. Okay. The boundary here is a first order phase transition. So the density of the particle going from across this line actually has a jump. And so the endpoint of the first order phase transition is called critical endpoint, and this is a crossover. So this is a schematic QCD phase diagram. And since we know the theory of QCD very well, so you ask, why don't we just put it on the lattice, despite it's a strongly interacting theory? But it turns out that only at the high temperature axis, lattice QCD can handle the calculation. In this half plane, lattice QCD basically doesn't give you much information. This is because QCD, lattice QCD at finite density has a so-called fermion sign problem. This is a simple explanation of the sign problem. So, so one thing you learned from your STEMAC class is that if the system is in thermal equilibrium, then the only quantity you only need to care about or you need to compute is the partition function. If you know the partition function, you know everything. And the partition function can be formulated in the path integral formula. It's a multi-dimensional integration. And the only method we now can handle multi-dimensional integration efficiently is the Monte Carlo. However, in this Monte Carlo simulation, people usually do important samplings. You create a small sample and say that this sample actually resembles the distribution of the whole population. However, if the quantity you are interested in, you measure the contribution from those important samples, and they actually cancel each other. So the information you extract from those important samples, at the end, is actually not important at all. Then you run into a problem. This kind of approach just doesn't give you some meaningful result. It's called the fermion sign problem. It's coming from different contributions from those important samples actually will cancel each other. There's a large cancellation going on. So lattice QCD forbids you to compute, to perform direct computation of QCD at finite density. But there is one way to get around it. That is, if you set the chemical potential to be purely imaginary, then you don't have the sign problem. However, the price to pay is that you have to do analytic continuation back. And there is some periodicity when you set the chemical potential to be imaginary, so you are only limited to this range when you do analytic continuation. So you only have access to mu baryon chemical potential over T is less than pi. And in the lattice QCD study, the critical endpoint appears to be either out of this range that you can probe, or your technology is not able to see the signal even though it's there. So in QCD, it's very hard using this approach. And it turns out lattice QCD has a cousin living in the coldest system on Earth. We say the quark plasma is the hottest thing on Earth, and the coldest thing on Earth would be cold atoms. Its cousin is a spin polarized unitary Fermi gas. Spin polarized means that it has different populations for spin up and spin down particles. So if you plot a phase diagram of temperature, it's normalized by the average chemical potential, and versus a spin imbalance chemical potential, then this is the phase diagram. It's a second order phase transition, then first order phase transition. It is actually similar to QCD when you have two flavors of massless quarks. Then this is, you've got similar phase diagram, second order, then first order. And in real world, in QCD, this second order becomes a crossover. So the two phase diagrams are the same, and they also have the same problems. In this system, when H is finite, you've got a sign problem. But when you set H is imaginary, then you don't have the sign problem. The question is, can you efficiently do analytic continuation back? It turns out we show that, yes, you can. So this is the range that it is accessible by imaginary chemical potential method, the range about here. And so we test the method by performing a mean field theory calculation that we can compute both in the real and imaginary axis. Then we just take the result in the imaginary axis as input, do analytic continuation back, and compare our result to the mean field the result from direct computation. And we found that if we do analytic continuation by the so-called Fateh approximates, then depends on how many terms we use in the fit. And we see some spread, which is corresponding to seeing something more singular over here. So it looks like this method can tell you the vicinity, give you some signal in the vicinity of the critical endpoint, even though we cannot clearly quantify what vicinity means. But this is encouraging. So the hope is we learn something from the hottest and apply it to the coldest systems on Earth. Maybe one day, and because the coldest system experiment can access directly to the whole phase diagram. And also, if we so one day, the hope is that we can learn something from the coldest and apply it back to the hottest one. Thank you.
I have a question about your chiral magnetic field. How does one realize this field in condensed matter, for example?
Okay, here's a material core bio semi-metal, which gives you massless 3 + 1 dimensional fermions. And so if you got this kind of system, then you can directly test.
I mean, how do you apply chiral magnetic field?
Okay, just you just apply a background B field, then see, say if you apply B field in the Z direction, you can see whether there's an electric current that induced in the Z direction.
So this one they said might be realized in quantum Hall effect in graphing.
This is in 3 + 1. This is in 3 + 1.
In 2 + 1, or which is the same as 1 + 1, because
so it can be
right, the topological insulator thing. The connection between anomaly and the transport phenomenon is actually tighter. It is fully understood, then better understood, I should say, because the system is simpler than here. So effectively, you are looking at the massless QED in 1 + 1 dimension. Okay, so you can relate to the electric current to the anomaly coefficient, and they are exactly, they can be exactly.
Right. Also, this is not, the transport coefficient is not corresponding to the quantum Hall effect, not on the Hall effect. Yeah, those are different observables. Yes.
So you consider the collision as you land the collision points, right? So then, does it mean that your system never reach equilibrium?
Okay.
Yeah,
I mean that your fireball. I mean,
Yes.
You really consider collision. I guess the fireball positive charge and the negative charge.
Yeah, very good. So I actually need collision to reach thermal equilibrium. You are right. But the claim is that it is possible that the transport coefficient doesn't depend on the collision. Just because if it is dominated or it's just the topological effect, like the triangle anomaly, then those loop corrections won't contribute. So that's our
equation don't, but equation do. Equation.
That's right. So we should put the collision term back to see whether there is some modification to the transport coefficients that we're interested in. But that is just because this kind of thinking behind that we sort of tune the collision to be smaller and smaller. You can say that's entirely small collision, but that's after the equilibrium is reached.
I think the statement is that as long as the interactions are renormalizable, the so-called non-renormalization theory applies. So as long as the collision is not too wild, then it's okay.
So we only need few collision to reach.
No. I think he could. The point in Junwei's approach is that the collision can be neglected if you just want to look at all those coefficients related to chiral anomaly.
Right. But you're right. We should first turn on the interaction, let the system reach thermal equilibrium or close to thermal equilibrium, then compute the transport coefficients. But in the computation, we can tune the strength of the collision to see whether it affects those transport coefficients. Yeah.
he's not looking at the so-called normal transport physics. Okay, he's looking at those transport phenomena particularly related to the so-called anomaly. So those
Right.
perceived, okay,
Yeah.
are collision receive no higher order correction from
Right,
collision.
right. Actually, those are dissipationist quantities. They don't generate heat.
Yeah, if you need that collision.
Right. From you can look at the divergence of the entropy current, and to show that those transport coefficients are not contributing to the entropy production. So, and this is just from hydro, so it's general. But the claim is because if it depends on collision, then naturally it should be related to the entropy production. So this doesn't, so there's something consistent here.
Can I ask
Yes.
another question? I
Yeah.
still try to see whether your system can be realized in real condensed matter
Okay.
system. But from what you just explained, or Professor Gao explained, it's very similar to enormous Hall effect.
For me,
Conductivity. In a sense, enormous Hall effect is supposed to be intrinsic. Okay, you can calculate
Okay.
without any collision. But to measure it,
what do you mean by anomalous Hall effect? I don't understand this one.
well, it's a kind of Hall effect.
So you send in a E field in the X direction?
No, it's a Hall effect with a ferromagnetic material.
yeah, without the magnetic field.
Okay, so you send a B field in one direction and look at the current.
No,
this
you send
direction.
electric field.
Okay, then that's different. Then that's different. Now we send in the electric field, and then you will have a.
But in a sense, there's electric field. Let's provide a bimagnetization. Exchange
Oh, okay.
electric field.
Okay, okay. But this is in 2+1?
This is three-dimensional.
Okay.
But you are always emphasized. You have been emphasizing three-dimensional.
Yes, because in 2+1 the physics is quite different. Basically, you don't get chirality in 2+1, but you get parity anomaly. I would like to learn more about this anomalous Hall effect later. Yeah. So the physics of this chiromagnetic effect is that you apply a B field and you induce current. And the chiromagnetic effect, vortical effect, is that when you have fluid, you stir it, so there's a vortex. Then the right-handed particle will go up, the left-handed particle will go down.
So maybe you should explain a little bit more your side of the experimental connection.
Okay.
So I think it's related to some Park-Gouin plasma result, this fireball.
Okay. So that's the charge separation picture.
Yeah, you showed the picture, but you did not elaborate at all.
That's right. Because using the chiromagnetic effect to explain this is kind of still controversial. But basically, it is related to the schematic picture that I showed you early on. If you have massless quark particles, in this case, we talk about U quark and D quarks. Those are, the mass is kind of small compared with strong interaction scale, like the QCD. So that's considered to be almost massless. So when you have U quark and D quarks, then their spin are going to be annihilated by the external B field. And so you've got a net chirality going in opposite directions. And it turns out you've got the U quark and D quark, and this kind of chirality flow. I'm sorry. So this is the vector current. The vector current is related to the charge current. There's a direct connection. So the net effect is that you have a charge current going along the B field direction, which is similar to the setup in the picture. So the idea is that there is a B field corresponding to the spinning fireball because it's still charged. And then you will drive a net charge current along the B field direction. And so you've got more positive charge particles on one hemisphere, let's say.
But you did not really tell us the B field, right?
Yes, B
I know
field
that
part
this will
is
be the strongest B field ever in the universe.